All right, welcome everyone to today's explainer. If you're gearing up for your Class XI computer science exams, you are exactly where you need to be. Today, we aren't just going to read about text. We're treating Python strings as physical, engineerable blocks of data. Think of this as your engineering masterclass. So, welcome to our metaphorical factory floor. In this explainer, we're going to learn exactly how these raw materials are measured, cut, inspected, and transformed. We are literally turning abstract code into a very tangible process. You know, I absolutely love kicking things off with this thought from Bill Gates. The great thing about a computer notebook is that no matter how much you stuff into it, it doesn't get bigger or heavier. It's just a great philosophical reminder of how seamlessly strings hold our vast amounts of data without breaking the physical bounds of our machines. They're completely weightless, yet infinitely powerful. So, here's our blueprint for today. We're going to cover anatomy and immutability, indexing and navigation, slicing and operations, the mechanics toolkit, and finally, custom engineering. All right, Section 1, Anatomy and Immutability. Let's get into the ironclad rules. Listen, if there is one single concept you absolutely must lock into your brain for your exams, it's this: immutability. Basically, once a string is forged in your computer's memory, its internal contents are permanently locked down. Its core identity simply cannot be tampered with after creation. And what happens if you ignore that rule? Well, if you try to forcefully pry open that lock and reassign a single character, say trying to change the very first letter to an A, Python instantly fires back a type error laser blast. It just shuts you down completely. Python doesn't negotiate here. You literally cannot change a string in place. Moving right along to Section 2, Indexing and Sequence Navigation. Let's talk about measuring these string blocks. So the really crucial point here is understanding this dual axis ruler. We use the len function to grab the total size, like 12 characters in this case. From there, those index numbers let us pinpoint individual characters, like zeroing in on a W at index 6, with absolute pinpoint accuracy. Let's briefly contrast these two measurement axes, because it's a total game changer. Positive indexing is just your standard left-to-right approach, always starting at 0. But negative indexing, that starts at -1 on the far right and moves backward. It acts as this massive shortcut. Think about it. When you're dealing with a giant block of data and you just need to grab the very last piece, negative indexing saves you from having to calculate the entire length first. It's so efficient. Now, you might be wondering, how do we actually move along that ruler? Well, we use loops. We've got the automatic for-loop conveyor belt. It just effortlessly extracts each character one by one and hands it right to you. Then we've got the manual while loop gear system, which gives you complete granular control over the index counter. Both of these mechanical traversals successfully extract each component, but you get to choose the exact rate machine for your specific problem. Okay, Section 3, Precision Slicing and Core Operations. Time for some cutting and assembling. Welcome to the cutting room. Slicing syntax uses start, stop, and step parameters, but you've got to pay really close attention to the precise cutting boundaries here. Remember this ironclad rule for your practicals, okay? The start index is always inclusive, meaning the cut starts exactly on that character. But the stop index, that is strictly exclusive. The blade drops right before the stop index. Oh, and with the step parameter, you can literally build a step skipper to just jump over characters entirely. Pretty cool, right? Now, what's genuinely fascinating is how we handle assembly. Remember our unbreakable rule of immutability, right? Because we can't change the original strings, operations like concatenation, adding strings together with a plus sign, and repetition, multiplying them with an asterisk, they actually build entirely new massive data structures in memory. The original blocks remain perfectly untouched and pristine. All right, on to Section 4, the String Mechanics Toolkit. Let's look at Python's built-in string methods. To make this massive syllabus of methods way easier to remember, we can actually organize them into 4 distinct engineering teams. We've got the inspectors for Boolean tests, the transformers for formatting and cleaning, the navigators for searching, and the architects for structural changes. Let's meet the teams. First up, the inspectors. You're going to want to deploy these methods immediately when you need fast Boolean quality control checks. Basically, they just return a simple true or false. Use them to definitively figure out if a string is completely alphanumeric, if it's hiding some sneaky invisible white space, or if it meets boundary conditions, like starting with a very specific prefix. Next up, when your data is just a mess, you fire up the transformers. These tools generate a brand newly formatted version of your string. So you can forcefully vacuum out unwanted spaces using strip, you can standardize your casing with lower or upper, or you could even swap out corrupted characters entirely using the replace machinery. And for the heavy structural changes, that's when you call in the architects. These are incredibly powerful for your exams. The split method acts almost like a controlled explosion. It forcefully shatters a single string into a list of separate words. On the flip side, the join method dynamically glues those list components right back together into a single string, using whatever separator you decide to define. Finally, Section 5, Custom Engineering and Palindromes. Let's build some palindromes. Let's take a look at reversal mechanics. A negative step of -1 slices right through the string backwards. It fundamentally acts as a reverser. You can use this custom engineering strategy to either print the string backwards in place using a loop or dynamically build a brand new reverse string in memory by concatenating characters one by one. It's super handy. So, this ability to read backwards leads us directly to the ultimate algorithmic question of the CBSE syllabus. How exactly do we program a machine to intelligently detect a palindrome? A word that reads the exact same forwards as it does backwards. Well, we don't just guess. We engineer a solution. We use this really elegant two-pointer approach. Step 1, we set indicator variables at both extremes. So index 0 and the final negative index. Step 2, we evaluate them for equality. And step 3, we methodically shift them inward, step by tiny step, until they either cross in the middle, which confirms symmetry, or they hit a mismatch. This completely illustrates the efficiency of that logic. For a word like Kanak, the pointers move inward in perfect harmony, returning true. But if the word is computer, the loop immediately terminates on the very first mismatched letters C and R. It spits out a false instantly. That saves tons of valuable processing power, rather than pointlessly checking the rest of the word. Wow, we have covered a ton of ground on the factory floor today. I highly recommend you screenshot this ultimate master cheat sheet for your exams right now. It maps out everything, from index limits and slicing syntax, all the way to your core toolkits. Review this carefully, and ask yourself, with this entire factory of tools now at your disposal, what complex data problem will you engineer a solution to next?